one emergency exit, so you can see them just in case. It's not going to happen. We haven't seen the bear in a couple of weeks, so we'll be all right. There, after the lecture, when you go out the door, you go to your left, you'll find the main intersection. There is one of those restroom trailers there for the public. As you go, before you reach that intersection, you'll see the food truck down to your left, and there'll be tables set out and stuff. And now it's excellent food. This katsu, they've been here a few times. It's a little slow. There's a lot of people, and we try to get them to go faster, but they refuse to prepare anything in advance because they're concerned about the quality of their food. And I understand that. We're all about quality and excellence up here as well. So if you can be patient with them, it's excellent, but it is really, really good food. I think if you order tacos and stuff, it might be a little bit faster. Lobster might take a little while longer, that sort of thing. Yeah, there's some fishing involved. And then after the lunch or after your meal, and if you brought your own food as well, we're perfectly fine with that. We love that. There's you sit at the tables. It's just nice as it gets dark. It's a sort of a nice convivial evening. Then you go further, you'll see to the left, well, to the right. To the right is the 60-inch telescope. That will be open. To the left across the Einstein Bridge is the 100-inch telescope. You can't miss it. And again, with a couple hundred people, it'll take some time for some of you. The lucky ones, the ones who are there first and faster get to get there. But also in the meantime, there are also several what we call amateur telescopes, but these are not amateur telescopes. I mean, these are pretty amazing stuff, trained on different objects. So they're wonderful, and you get to see different things in the sky. Pretty much on each of the telescope, you get to see whatever they're looking at. So we have the other, Los Angeles amateur astronomers with their telescopes, and they're pretty amazing. You'll see that. So anyway, that's it. I'm going to now introduce Sam Hale, who will then introduce Wendy. And thank you very much.
As Dan said, my name is Sam Hale. I'm the chairman of the board of trustees of the Mount Wilson Institute, which runs the Mount Wilson Observatory. And I am blessed to be the grandson of George Ellery Hale. This is an incredibly exciting weekend for me personally, because this weekend, starting on Thursday evening, 40 plus members of the extended Hale family came from all over the country to celebrate the 154th birthday of George Ellery Hale, June 29th, 1868. And we know what an incredible person the man was. And in our get-together on Friday, yesterday, we had a wonderful tour of the campus by 4 campus docents. That afternoon, we had a tour of my grandfather's solar laboratory, and telescope that he built starting in 1924 after he had to retire as director of the Mount Wilson Observatory due to declining health. Last night, we had a lovely dinner in the Athenaeum, which is the faculty club of Caltech. We were blessed to have Tom Rosenbaum, the president of Caltech, share some thoughts with us on George Ellery Hale and his instrumental role in the founding of Caltech as we know it today. And then we had a talk by Dr. Ed Krupp, who is the executive director of the Griffith Observatory in Los Angeles, which I know you all know and have been to many times, I'm sure, has more visitors than any other observatory on Earth. An incredible outreach, public outreach of astronomical education. And tonight, we're going to culminate this with a talk by Mount Wilson's wonderful friend and my wonderful friend, Dr. Wendy Friedman. One thing that I want to do before we start is I'd like to have all of the assembled Hale family get up. The reason I want all of you to see these people is because in these 2 days that we've met together, for the first time, this has been the first time, at least, we've had this type of a family reunion. And I want you to know that this is a family that has dedicated themselves to the preservation, the enhancement, and the future prosperity and expansion of our role as Mount Wilson Observatory in pushing forward the legacy of George Ellery Hale. And these people are going to do it in the next generation. So I just want you to know that you've got a bunch of dedicated people. And I can't tell you what that does for me. You know, June was a seminal month in the life of George Ellery Hale. To start with, he was born on June 29th, 1868. I mean, isn't it incredible that here I stand, his grandson, in 2022, and my grandfather was born in 1868. Wow, that's something. And so that's the first June happening in his life. Secondly, it was June of 2003 that he first came to Mount Wilson. And there's a wonderful picture of him standing at the edge of the mountain with binoculars and his tall rattlesnake-proof boots and a big hat with binoculars looking out over the horizon and surveying the surrounding basin. And the other great June in his life was June of 1907, when he discovered magnetic fields in sunspots, one of his great discoveries. And here we were commencing this wonderful reunion at the end of June 2022 to celebrate it. Well, tonight, this is the culmination of this wonderful get together, and I think it's going to be another incredible high point with Wendy Friedman, who is going to share her thoughts on the contributions of George Hale to cosmology. Wendy was educated, got her PhD at the University of Toronto in 1984, and then became a fellow at the Carnegie Observatories in Pasadena, also in 1984, and then joined the staff permanently in 1987. In 2003, she was named director of the Carnegie Observatories and held that post until 2014. And from 2003 on, she was the founding chair of the giant Magellan Telescope project, the 25-meter optical telescope that Carnegie and a consortium of partners are now building in Chile. And in 2015, she was named a university professor, which I will share the meaning of with you in a moment, at the University of Chicago. Wendy's interests are observational cosmology. She was a primary investigator of a team of 30 astrophysicists in the Hubble Key project that studied the expansion of the universe, and she currently studies the past and current rate of the expansion of the universe. And she is now a primary investigator of the first cycle program of the James Webb Space Telescope, which I hope she's going to share a little bit with us, to measure the Hubble constant to a percentage level precision. I was trying to get my arms around what I could say about Wendy. And I thought, I'm going to call Tom Rosenbaum, the president of Caltech, and because he knows a bit about the lady. And because I was looking at the CV, I mean, look at this list of honors. I go cross-eyed trying to go through all those things. And I called Tom and I said, give me the essence of why she is as great as she is. And he said three things. She said, she is so far ahead of the curve in research. And she says, on top of that, she has incredible integrity to follow the data wherever it takes her. And on top of that, an incredible administrative ability that you don't find with an academic, a researcher, and a scientist all in one role. So I was thinking about that and I said, that sounds familiar. That sounds like George Ellery Hale.
Yeah.
Wendy has been a special friend of Mount Wilson. We're deeply indebted to having her here with us to describe George Ellery Hale's contributions, not only as a scientist, but as a human. And I just can't thank her enough for joining us. And I think we're going to learn how it was that George Ellery Hale was able in this place to create the second Copernican revolution on Mount Wilson. Wendy.
Well, thank you, Sam, for that incredibly generous introduction. It is an honor for me to be here this evening and to be speaking with so many members of the Hale family. I began my career in astronomy in the early 1980s, and George Ellery Hale was a name that I knew about when I was an infant in astronomy. And coming to Pasadena was like a lifelong dream, and to be able to come to two mountains, Mount Wilson and Mount Palomar, where George Ellery Hale had built his telescopes and where cosmology started, was just for me a dream that I could never have imagined that it would come to pass. And when I became the director in 2003 of the Carnegie Observatories, the person that I most often thought of was George Ellery Hale. And the kinds of difficulties and the kinds of challenges that he faced in creating what we're sitting now under the auditorium on the mountain where he first built these telescopes was, it takes a certain kind of person to do that, very special kind of person. And I'll describe a little bit. Do I have a pointer, by the way? Is that possible to have? No, it's okay. I'll point. The old fashioned. I still have an arm. And there really is a direct line between the telescopes at Mount Wilson and the giant Magellan Telescope that's shown over there on the right that we're now building in Chile. And the fact that the Carnegie Institution has led these efforts for over a century is really due to one man, and that's George Ellery Hale. So it really is an honor for me to be speaking here tonight, and I thank you again, Sam, for this invitation, and I warmly greet all of George Ellery Hale's family. It's a treat for me. So as we've heard, George Ellery Hale was born in 1868. He was in Chicago at the time where he read in the Chicago Tribune about a gift that Andrew Carnegie was giving to what became the Carnegie Institution of Science. And George Ellery Hale was influenced by Daniel Burnham. He was an architect in Chicago. And apparently in 1910, he wrote, and probably did before that, oh, thank you, a statement that George Ellery Hale was very fond of quoting: make no little plans. And we can see that George Ellery Hale really took that very seriously. They have no magic to stir men's blood and probably will not themselves be realized. Make big plans, aim high and hope and work, remembering that a noble logical diagram once recorded will never die. but long after we are gone, will be a living thing asserting itself with ever-growing insistency. And if there's one man who could really say that that came to pass, I think it's George Ellery Hale. Here's the picture that Sam just told us about of George Ellery Hale when he came out to Mount Wilson in 1903. And he recognized that this was a special site. And the conditions on this mountain, the stability of the air on this mountain, what astronomers refer to as astronomical seeing, is quite phenomenal. And if it weren't for the lights in Los Angeles now, it would probably still be one of the better sites in the world for all types of astronomy. Still superb for interferometry and other kinds of techniques because of this very stable atmosphere, an inversion layer here. So I should also mention that before he left Chicago, George Ellery Hale built the Yerkes Telescope, a 40-inch refracting telescope in Wisconsin that the University of Chicago ran until just a few years ago. Came out and built the solar tower where he made the discovery that on the sunspots of the sun, he could actually see the split in spectral lines that indicated that there was a magnetic field on the sun. He was the first person to make that discovery. He was responsible for building first the 60-inch telescope, and those of you who haven't seen it yet, we'll see it this evening. Before the 60-inch was even completed, and this for me as director, when I thought of this, we were trying to build the giant Magellan Telescope, before even having all of the funding in place, before having all of the construction in place, he was already trying to build the 100-inch telescope. And then he was the driving force between building the 200-inch telescope at Mount Palomar. It's a phenomenal legacy, and I don't think it will ever be surpassed. Here's Hale standing with Andrew Carnegie, and this Andrew Carnegie is the person who had the idea that if you could fund scientists to do science and give them resources, that really interesting things would come of that. And Hale had read about this again in the Chicago Tribune, contacted Andrew Carnegie. It was a $10 million gift in 1902. And the idea was to encourage investigation, research, and discovery in the broadest and most liberal manner, and the application of knowledge to the improvement of mankind. So we'll notice all the mankind's in here, and it was mankind in there, but it's changed. Some things have changed. Thankfully. So here's the solar telescope, the 60-inch telescope, the 100-inch telescope, the 200-inch telescope. And if that's all that he did, it would have been unbelievable. But there's a huge legacy of George Ellery Hale elsewhere, both in Pasadena proper and also within the astronomical community. So the Civic Auditorium, George Ellery Hale felt when he came out in 1903, Pasadena was a sleepy little town. It had no paved roads or dirt roads. And the idea of building up Pasadena was very appealing to him. He brought out architects that designed the Pasadena Civic Auditorium, the Pasadena City Hall, and he convinced Henry Huntington to locate the library and gardens in Pasadena. Henry Huntington wanted to put his art collection, give it to the LA County of Art, and Hale convinced him to do that in Pasadena. And then he had been on the board for what was called the Throop Institute. It was a secondary elementary school. I think there were 18 students. And he brought out Noyes and Millikan, and the three of them founded the Caltech Institute of Technology. The headquarters of Mount Wilson, or what we now refer to as the Carnegie Observatories, the address at 813 Santa Barbara Street. Here's an original building. This is the back of the building now, where still the Carnegie Observatory has its offices, and the telescopes in Chile are run out of the Pasadena office. And these are the offices of the astronomers in Pasadena today. The Las Campanas Observatory was a natural extension. Once the lights in Mount Wilson got very bright, the Carnegie Institution decided to move southward and built a series of telescopes on Las Campanas in Chile. And that's the most recent construction, the Magellan telescopes, twin telescopes, 6.5-meter telescopes at Mount Wilson. I wanted to mention, let me show you a couple of pictures of George Ellery Hale and John Muir and Carnegie at Mount Wilson. And there's a quote by John Muir that I really like, which is when we try to pick out anything by itself, we find it hitched to everything else in the universe. That also, I think, really lends itself to a description of George Ellery Hale's influence and what we've learned in our field. So the 16-inch telescope was the telescope that Harlow Shapley, who eventually became the director of the Harvard Observatory, made his discovery once the Mount Wilson telescope was working up here. By the way, they used mule trains to bring up the pieces of the telescope as it was being fabricated. And the prevailing idea at the time was that the sun was the center of the universe. And in the 1500s, we learned that the Earth was no longer the center of the universe, which had been the idea for 2000 years, that the Earth was the center of the universe and the sun and the planets all revolved around the Earth. So Copernicus told us that the sun, in fact, was the center of the universe. And Harlow Shapley was able to show that the sun was not at the center of the universe. So this idea had held sway for 400 years. And using the 60-inch telescope, Harlow Shapley was observing a collection of objects known as globular clusters. These were objects that do have a spherical distribution on the sky. And what Shapley expected to find when he was studying the distribution of these objects was that the sun would be at the center of that distribution. But in fact, he found that the sun was about 2/3 of the way out from the center. The sun is not at the center of the universe. That's a phenomenal discovery. It really was, since the time of Copernicus, what our view of cosmology had been. But very soon after, Edwin Hubble began to use the Mount Wilson 100-inch telescope, and Hubble discovered that there are other galaxies in addition to our Milky Way galaxy. There are about 100 billion other galaxies. And not only are there 100 billion other galaxies, but these galaxies are taking part in an overall expansion of the universe. And this is an idea that given the expansion of the universe, if the universe is expanding now, then in the past, it must have been closer and closer together. And with the development of the general theory of relativity by Albert Einstein in 1915, these are the observations that led to what we now call Big Bang cosmology. A universe that is expanding had a hot, dense beginning, and this Big Bang explosion of space, with galaxies expanding ever since then. And this is the place where these observations occurred. Now, one thing that I did want to mention is that there's a wonderful, wonderful video of the making. It's called The Journey to Palomar. It was done by a husband and wife team, Robin and Todd Mason. Some of you may have seen it. That tells the story essentially of George Ellery Hale and the making of these telescopes. I highly, highly recommend it. It's one of the most moving documentaries I think I've ever seen. And Todd Mason is with us this evening also. This is quite an incredible collection of people here tonight. So here's the plate that Edwin Hubble took at the 100-inch telescope. He's put an exclamation here beside the letters VAR. And what he means is that there's a variable star here. And he had crossed out an N. He thought this was perhaps an object called a nova, which is a different kind of object in astronomy. What he realized on this particular plate was that there's an object, we refer to these as Cepheid variables. These are stars that have, now we understand, stars that have atmospheres that are pulsating in and out. And the rate at which they're doing that is related to how bright the star is. What that means is that we can use that relationship to gauge the distance to galaxies. And this is the first inclination that this would be possible. So if we look out at the sky tonight, we see stars in a two-dimensional distribution on the sky. We have no idea whether a star is bright because it's nearby, fainter star might be farther away, or whether it's intrinsically brighter. We just have no information without knowing the distance to the star. And that's what Hubble's discovery, that's why he was excited, why he marked it with an exclamation mark, was realizing that within, this is the Andromeda Nebula, it's at those times, these fuzzy objects were called nebulae. We didn't know about galaxies until Hubble discovered them. There are many of them in our own Milky Way galaxy, and there'd been a debate about what the nature of these nebulae was. Were they regions in our own Milky Way where new stars might be forming? See these little bit spiral arms. There's some much bigger examples of spiral nebulae. So this could have been a region where gas and dust were collapsing and forming new stars, or as Hubble was able to show, a region that's very distant, a galaxy in its own right, not unlike the Milky Way. And once he was able to show that, he could, it completely changed our perception of the universe, its size, its age, and so on. So here's Edwin Hubble now examining plate in 1952. So the detector at that time were these large glass plates. We didn't have electronic detectors like we do now on our phones, charge a couple devices that allow us to measure very faint light levels with much higher accuracy than was available to Edwin Hubble or George Ellery Hale, early astronomers. But in any case, these are the data that allowed him to make this observation. This was 1923, October, so we're talking a century ago. And of course, today we have the Hubble Space Telescope named after Edwin Hubble. They're similar size. The Mount Wilson 100-inch, the Hubble Space Telescope is also a 100-inch telescope, but it's operating above the Earth's atmosphere and allows us to get much sharper images without the interference and the turbulence in the Earth's atmosphere. Here's the diagram that allowed Hubble to tell us that the universe is expanding. And what he's showing is that the velocity here, the velocity at which a galaxy is moving, and most galaxies are moving away from us, it turns out, is related to how far away the galaxy is. So you can see, even though there's scatter in these data points, so each of these are individual galaxies, there's a clear correlation. The farther away a galaxy is, the faster velocity that it's moving at. And this was the observation that indicated that the universe is expanding and gave rise to our Big Bang cosmology. So here's an example, a better example of a spiral galaxy with spiral arms. Our own Milky Way galaxy also has spiral arms, and as does Andromeda. Here's Albert Einstein. He came out to Pasadena in 1931. He wanted to meet this guy, Edwin Hubble, who made these observations. And he's in the library at Santa Barbara Street, which is the Carnegie headquarters. We affectionately refer to our buildings by their street addresses. Don't ask me why, but that's what we do. And he's drawing his famous equation here on the blackboard at Santa Barbara Street. He also came up to Mount Wilson. So here is Hubble on the catwalk of the 100-inch telescope, along with Edwin Hubble and Adams, who was director at that time. So Einstein peering out over Mount Wilson here. And here is Einstein explaining to Edwin Hubble how you look through the telescope. And Edwin Hubble is explaining that in order to observe, you have to have a pipe. A few things have changed since that time. So the Cepheid variables that I mentioned to you, the discovery of how they could be used to measure distances to galaxies, that was enabled by observations that were analyzed by Henrietta Levitt. She was an astronomer working at the Harvard College Observatory. This is the relationship that now bears her name. It's called the Levitt Law, along with, there's a Hubble law. And Levitt discovered this relationship between how bright a Cepheid is and how fast its atmosphere is moving out. And this is what we still use to this day. One of the best ways that astronomers have of measuring distances to galaxies is making use of this Levitt relationship. And when the Hubble Space Telescope flew in 1990, one of the key projects was designated for the telescope with measurement of the expansion rate of the universe. And what happened since the time of Hubble was that there was a big debate. Again, there we had a lot of debates apparently in astronomy, but there was a discrepancy that had arisen. People were measuring different values of this Hubble constant and couldn't settle on what the actual expansion rate is. And that's important because the rate at which the universe is expanding allows us to gauge both the age of the universe, how long it's been expanding for, as well as the scale size of the universe. And essentially, we can make measurements in our local region of the Milky Way, where we can measure stars like Cepheids and other kinds of stars using a technique called parallax, geometric parallax, which just makes use of the fact that the Earth is orbiting the sun, and we can observe stars at different vantage points through the orbit, and then just use straight geometry to determine the distances very accurately. So we do that locally, and then we build the distance ladder to move out into space, more distant regions. So I also wanted to acknowledge this evening my closest collaborator, Barry Medor, who's also my husband and also father of my children. We agree that one of the best outcomes of our collaboration is our kids. And one of them sitting here today, and he probably wants to kick me because, but this is not the only family reunion of the Hale family this evening. We're also having a reunion of our family, which is really nice for me too. So measuring the Hubble constant, what we can learn about the evolution of the universe, expansion of the universe, turned out to be really very difficult, and for reasons that weren't well understood at the time. So here's Edwin Hubble's measurement of the expansion rate. He got a number of 500 units or kilometers per second per megaparsec. That's a mouthful, and I won't test you on it later. So it was a high value. Walter Baade, who was also working at what was called the Mount Wilson Observatory at the time, the Carnegie Observatory, had a new measurement in the 1950s, which required a revision of the distance scale by about a factor of 2. And then the numbers started to converge between about 50 and 100 in these same units. But that's a big difference, a factor of 2. We didn't know how old the universe was, better than a factor of 2, or how large it was, the visible universe. And people argued about whether the universe was 10 billion years old or 20 billion years old. And there didn't seem to be a way of resolving that. These are some of the measurements in the 1970s, 1980s to 1990, showing this scatter and the discrepancy between 50 and 100. And here's what we're doing now. We're measuring Hubble constants that have a much smaller scatter, and using the same kind of technique with the Cepheid variables, we get a value of about 73. And that's the value that we got with the Hubble Space Telescope, the key project that I led in the 1990s and early 2000s. And this is a value that is coming from measurements of tiny differences in temperature in the background radiation from the Big Bang. And I'll mention in a moment, that could be a very interesting difference if it's real. But what it requires is that not only is this now smaller difference significant, actually telling us something real, but the uncertainty in the measurements has to be about the size of the width of the line itself. So that would be a pretty large jump in accuracy in the last couple of decades. And that's what we're working hard to establish right now. So the hero on this to date has been the Hubble Space Telescope, and what allowed us to get above the Earth's atmosphere. Showing here, this is Hubble's original plot we saw a few moments ago. And this is the plot we published, our key project, using the Hubble Space Telescope and many different methods for measuring distances. And here's where Hubble's original data would fit in this first tick mark here. So we're now able to make measurements out much farther in the universe. And the measurements, this is showing the values that have been attained since the time of the key project. And all of these are based on these Cepheid variables that I've been telling you about. Here's our values in the 72. And then that's remained pretty constant, sort of mid 70s, mid to low 70s. But what has really changed over the intervening time is that the uncertainty, the size of these error bars here has continued to shrink with time. Now, the other method that I mentioned is measuring the tiny differences in temperature. So these different colors represent different temperatures or different densities of material in the early universe. And you can use this information to gauge what the expansion rate of the universe would be today with a model of cosmology. How is the universe evolving with time? I don't know if you can see here, if anybody can recognize this in this microwave background pattern. Anybody see anything? Well, there's an S and an H. You see them now?
Oh my God.
What do you think? Pretty prescient of the microwave background. You like that one? I was realizing, so I was thinking about this talk, and wow, that fits. Now, here are the values of the Hubble constant that you get using these microwave background measurements. And starting in about 2003, there was a telescope, the Wilkinson microwave anisotropy probe, measured a value about 71, I think is what they got. Looks higher here in this plot, but very consistent with what we got for the Key project. And then those measurements became more and more accurate. You can see the error bars are shrinking again. And there's a satellite called Planck. It's a European satellite that now has a really precise measurement of the Hubble constant. It's coming in at 67 in these same units. So 73 or so with the Cepheid, 67 with the microwave background. And the precision here is better than 1%. So this is what we're trying to understand. Is this a significant difference? You see, the error bars aren't overlapping. So if the error bars are real, if these are the true uncertainties, then what it is telling us is that the model that we have that describes the microwave background observations would be incomplete. And there's new physics from the early universe that we would learn about by making this comparison of what the expansion rate we're measuring locally is compared to the early universe where this microwave background was being emitted. We can finally see it after it's scattered for the first 380,000 years. So this is what we're trying to understand. The Planck observations early in the universe are giving 67. H naught here represents the Hubble constant. The Cepheids give 73. And could something have happened in the intervening time, or even before we can make the first measurements of the microwave background? So now I want to say a little bit about the giant Magellan Telescope, which I really think is the heir of what George Ellery Hale started in our quest to build bigger and bigger telescopes. So of course, the bigger telescope you have, the bigger mirror is like a light bucket. You can collect more light the bigger your mirror, which is why astronomers are excited about building larger and larger facilities. This is a telescope that will have 7 mirrors, each of which is 8.4 meters in diameter. They have to all work together. So the 100-inch telescope is a single mirror. You bring the light together at a single focus. And all of these mirrors have to bring the light together to a common focus to make use of the resolution that is in principle offered by a telescope of this size. So the resolution increases, the ability to see fine detail increases the bigger your telescope. The sensitivity increases so you can see farther objects or fainter objects. It has a novel technology for making the mirrors. These are constructed at the University of Arizona football stadium. Underneath the football stadium, we joke sometimes that some future civilization will think that football stadia are really important because there's all this equipment. So you can see the 7 mirrors here, 6 in a circle, 1 in the center, and there's a cluster of 7 mirrors, secondary mirrors near the top of the telescope, and each one of those will correct one of the primary mirrors. So it has a conjugate mirror in the primary mirror. We've constructed now 5 of the cast 5 of the mirrors for this telescope. There will originally, eventually be 8 of them. There'll be a spare. It takes 4 years to complete one mirror, from the casting, polishing, and final completion of the mirror. So you can see the dome has a different shape. We refer to it now as an enclosure. We don't have these nice dome-shaped enclosures anymore for our telescopes, and they're open to the air because having the ambient air blow in keeps the mirrors at ambient temperature, so they're not fluctuating in temperature, which causes turbulence on the mirror. And the GMT is going to have 20 million times more sensitivity than the human eye. Pretty spectacular increase. And if you were observing in Santa Barbara, you held up a dime in San Diego, you could resolve the face of that dime. That's what the resolution of this telescope will be. It's incredible. You could also view a candle on the moon. If there was air on the moon and we could actually light a candle, that is, the GMT would be sensitive enough to see that. These are some simulations. So if you notice, this is a region, a star cluster in a nearby galaxy. And so you can see these blobs here. And this is the what we would call a good seeing night on an Earth-based telescope. So watch these blobs here. And the next image that I'm going to show you is an infrared camera on the Hubble Space Telescope. And you can see when you get above the Earth's atmosphere that a lot more detail shows up. You can see fainter stars. And the next image is what the James Webb Space Telescope will see. Now, this is the telescope I'm going to describe more of in a moment. This is a successor to the Hubble Space Telescope, and it was launched on Christmas Day last year. And it is about to release its first science images next week. So you will want to stay tuned for this. But now look at the fine detail that has shown up here, those 4 original blobs. And this is what the GMT will see. So the GMT is going to have 10 times the resolution of the Hubble Space Telescope, which is our benchmark for what high resolution is right now. It's pretty phenomenal. So it's due to be constructed, we hope, in completed construction in the early 2030s in Chile. So now if we get back to the question that I posed, is there new science that we've missed in these observations of measurements of the expansion rate of the universe? And I'm not going to go into detail of this. I'll be glad to answer questions at the end. I just want to say that what we're trying to do now is to build a new distance scale from the ground up. This is something that Barry Vidor and I have been working on for just over a decade. And we're using a different kind of star than the Cepheid variables. Why do we want to do that? Well, if there's something we don't understand about the Cepheids, we can make the measurements as many times as we have the energy for, or they'll give us space telescope time for. And if there's an error somehow or something we don't understand about the Cepheids, we're going to make that error over and over and over. We want to do this independently in some way that doesn't depend on the Cepheids. So we're using another kind of star. It's called the red giant branch star. This is a phase of stellar evolution that our own sun will go through eventually when it exhausts all of the hydrogen that it's now burning in its core. And the nice thing about these stars is that they reach a luminosity that is the same luminosity for all of these stars. And so it really is like a standard candle. Unlike the Cepheids that are pulsating and changing their brightness, this has a stable luminosity that we can measure. And when we go out to the outer regions of galaxies, the Cepheids are located in the disks of galaxies because they're young stars, they're new stars that are forming. And so that's where they are. That's where we have to observe them. And the problem with the disks is because of all the new star formation, there's dust, there's gas, and it leads to problems in the measurements. And so these giant branch stars have the advantage we can observe them way out in the halos. You can't see this at this contrast, but there are tens of thousands of stars out here that we can measure very, very accurately. And then we tie into objects that are called supernovae, these very bright objects that we can observe at essentially half the radius of the observable universe or even farther. And I just mentioned some of my Carnegie colleagues here. Here's Mark Phillips and Chris Burns, who have been part of this project for over a decade now. And so what we found was that when we made these measurements, here are the Cepheids, here is the microwave background, we thought we would find one or other of the measurements that either 73 or 67, but we landed in the middle, right in the middle. As Sam said, that's, you know, that's where the data take us. That's stuff. Sorry, we can't do anything about this. But I actually have had senior astronomers say, well, you really should be one or the other, but you know, that's not what the universe is delivering to us right now. So we'll see what happens with the James Webb Space Telescope, which is what I'm really excited about for the future. So James Webb, as I mentioned, was launched Christmas Day, last Christmas, and it's about to release its first science observations a week Tuesday. So I think you'll want to stay tuned for this. I think it's going to be pretty exciting. This is a telescope. It's a 6.5 meter telescope. Hubble's a 2.5 meter telescope. It has 18 mirrors. These are made of beryllium and coated with gold. This telescope, I first heard about 25 years ago. I was on a scientific advisory committee that had been charged with coming up with what would succeed the Hubble Space Telescope. So this was the idea. And a few astronomers were asked to go to the Goddard Space Flight Center. We were giving some advice, scientific advice, and we first heard about this telescope that would have to unfold its mirrors in space. It was going to fly 1 million miles away, 1 million miles from the Earth, unlike Hubble, can't be serviced. It would have a sunshade here that would have to unfurl in space. These things, each of the 5 layers of this sun shield is about a width of a human hair, has to unfurl in space and then be locked into place. And the astronomers in the room looked at each other and said, this is insane. It will never work. And it worked. Yeah, it's amazing. It was a picture perfect launch. It could not have gone more flawlessly. And I think they said there was something like 100 single point failures. We were literally waiting with bated breath for each one of these things to unfurl. But it made it. It's 1 million miles away now. So here is, here's the moon. This is Hubble's orbit. Hubble's in a low Earth orbit, but well, here, 400,000 kilometers above the Earth. And this, the James Webb Space Telescope is now about 1 million miles from Earth. And it's a place called the L2 Lagrangian point. I'm not going to ask you about that later either. But the first images, they took up a star. There are 18 of them here that just happens to magically match the number of mirrors there are. So it was actually one star, but it was all over the place. They had to spend weeks fine-tuning the positions of the mirrors so they knew where each of these stars should go. And eventually they were able to focus it into a single image. And that image, with a calibration image, turned out to have galaxies in it that had never been seen before. So even the test images now are proving to be just spectacular. Here's an image that was taken by the Spitzer telescope. It's a 24-inch telescope in space, a mid-infrared telescope. Here was, again, this is a test image from Webb and the mid-infrared instrument taken in May. Now, why is Webb so interesting? Why do we want to observe in the infrared? Here's a picture. This is the Eagle Nebula. It's a region in the Milky Way where it's essentially a stellar nursery. New stars are being born in these pillars here. They're, I think the number is something like 6 trillion miles high, these things. And that's small by astronomical standards. This is a small region in our own Milky Way galaxy. And you can see these dark patches here. We can't see any stars in this nursery. But when we observe in near infrared light, suddenly you can start peering through the dust and you can start seeing where there are stars that just are not visible in optical wavelengths. And then in the mid-infrared, when you go to even longer wavelengths, you start seeing the dust radiating itself, and you can learn about the dust properties. So it has this incredible capacity. Also, because the universe is expanding with time, as we look farther and farther back, we're seeing earlier in the universe, as the universe was when the light left those objects, because light travels at a finite speed. That's something that Albert Einstein taught us. And because of the expansion, the wavelength of light is being stretched and it's being shifted to the red. And so we can observe farther back in time when we have access to an infrared telescope. So with the Webb, we're going to be able to witness for the first time the first galaxies that are forming in the universe. And with Hubble, we can take really faint, deep images. We see tiny little smudges of galaxies that are very far away. And we know we formed, the galaxies formed, galaxies around us formed, but we'll actually be able to see it happening for the first time at high resolution. So it will be like a time machine looking back in time. We also expect it's going to help us improve our measurements of the expansion of the universe and get at this question, this tension between the early and the late universe. And so as I mentioned, we've used Hubble to date. We are about to use the James Webb. Our group got time in the first cycle with James Webb, and we'll be observing starting this November for about a year, different objects, Cepheids, and these red giant branch stars, and another type of star. So we should be able to understand, is this difference real, or is there something wrong with the Cepheids? And having spent a lot of time working on Cepheids, it'd be a shame to find out if there's something wrong with them, but if there's something wrong with them, we're going to learn it. So I think it would, you're very interested to stay tuned. As I said, in a week, we're going to get the first images from the James Webb Space Telescope. In the 2030s, we'll start getting images from the giant Magellan Telescope. And I want to, again, pay tribute to George Ellery Hale and for his scientific vision that began this whole quest. So thank you very much.
Repeat them because we don't have.
So I'm happy to answer any questions, and I'll repeat them if so we can hear. Oh, thank you. Thank you. Yes, in the back. I think it's likely to be an even balance because you can do different things. So the Giant Magellan Telescope is a 25-meter equivalent telescope. We have no way of putting something that large into space right now. And as I said, the bigger the telescope you have, the bigger the light bucket, the higher sensitivity you have. And particularly for taking spectra where you can disperse the light into different colors or different wavelengths, you need high sensitivity to do that. So one of the, I think, really exciting things for both James Webb and the GMT and other big telescopes is going to be looking for planets that are similar mass to the Earth. And you're going to need a telescope like the GMT that has high resolution to get the velocity resolution to measure the motion of essentially the reflex motion of the star due to a planet with the mass of the Earth. And with JWST, we're going to have infrared capabilities. So the spectra that you get covers a larger range. You need both optical and infrared information. We're going to be able to see, for example, if there's water, carbon dioxide, methane, ozone, and actually look for biosignatures, signatures of life. So it's, I think, one of the really exciting things that these new telescopes are going to do, and they're going to be very complementary to each other. So I think that's going to continue for a while. Another question in the back. Sorry, I couldn't hear that. Can someone repeat that for me?
Did you say that one of the southern layers are covered with gold?
Yes, I did say that. It's a very, very thin layer of gold, but they are covered with gold. And that works very well for infrared radiation. Yeah, they are covered with gold. Thank you for that question. Yes. So several levels are going to answer that question. So one of the dangers right now, not so much for GMT, because the big telescopes are going to look at very small areas in the sky. But there's a telescope called the Reuben Telescope, which is being constructed right now. And it's going to have a 6-degree field of view on the sky. And it's going to be surveying the sky every night, over and over and over. So scanning and covering the sky to very high depth. And so these satellites are going to be a source of noise for these big areas. They just go across and they streak across, and there's no way of knowing exactly where they're going to be or how you could take them out. They're just, they're going to be a dreadful source of noise. Now, Elon Musk himself has offered to try and find a solution to coatings for these satellites so they're not reflecting as much. And so he's experimenting with that. He's doing it with his own funding. He's not expecting astronomers to do it. But I think the bigger danger is that the genie is out of the bottle. So even if Elon Musk is able to help, other countries are not going to be doing that in the future. And they're just going to be more and more and more of these satellites. So it is a real concern. It's for the future. There's no question. Yeah.
Are these big projects that they will be country collaborations or?
Yeah, so the question is about whether these are global initiatives and how countries are collaborating or not. I think it's been remarkable. I think if you look at, I'll give you GMT as an example. So we started off as a US-based collaboration with only 3 partners. And now we have Australia, South Korea, Sao Paulo, Brazil, Chile, and most recently the Weizmann Institute in Israel. So there's been great collaboration, and that's been true for all of the other big telescope projects, certainly within Europe. So we used to joke, I mean, before we put our collaboration together, and within Europe, countries that used to go to war with each other are building telescopes together, which is pretty remarkable. So James Webb is another international effort, and you've got private institutions, private universities, state universities, governments. I think it's a real example that when people put their mind to big things, they can do them, and that global cooperation is something that is fantastic when it happens. We can do this as a species, and we need to find other ways in other areas to do more of it. Yes.
You said that with Hubble's and Shapley's work, we have a whole new view of where we fit into the broader universe. Any guesses as to what, if we were sitting here 100 years from now, we say, we learned this in the last.
So what will we learn in the next 100 years? And I think that is one of the exciting things about planning to build these new facilities. So we had no idea what was going to come of Hale's vision, right? And so why we get excited about these new capabilities is every time we have built a new kind of telescope, either wavelength coverage or bigger area or some new facility, we've made new discoveries. That, without exception, that has always happened. And so now with these really big these extremely large telescopes and things like James Webb that have new capability, my hope is that we will find something that we have no way of predicting right now. But then I have no way of predicting it, so I can't answer your question. But I hope that's what we find. Yeah.
So as you measure galaxies moving away in the universe, say the universe is expanding, this notion that this empty space previously and the Big Bang is populating it, and celestial bodies moving in empty space. What is the universe expanding into?
Yeah. So what is the universe expanding into? And this is something that it's a hard concept to think about, right? What is, and essentially the Big Bang was an explosion of space itself. So space is being created as the universe is expanding. And so it's not like a bomb that goes off where it has a center and it's expanding into something else, right? And that's a hard concept of what does that mean? And the best analogy that I like, and it may or may not work for you, is that, it's, you know, if you have a surface, so just say this water bottle here, right? And the surface itself is 2-dimensional. So if I'm an ant on the surface, I can crawl all over the surface and there's no edge to the surface itself, right? Just the surface has no edge. It's a 2-dimensional, you can crawl anywhere on it. And general relativity is a four-dimensional theory, Einstein's theory. So there's 3 dimensions of space, 1 dimension of time. And so analogously, there is no edge to this space-time. And so mathematically, this is perfectly consistent. It makes sense, just hard to visualize. But if there's no edge, and it's, Stephen Hawking once put it, there's nothing north of the North Pole. It's not a question that makes sense. Does that help? Okay, another question in the back, and there's one here too, but you go ahead. So there's a time allocation committee. How do they decide who gets time? So as you can imagine, we wait for 25 years, which is what it took to build Webb. And there are a lot of people who want to use it. And so what happens is they create a committee that's anonymous, and you submit proposals, and they've now changed the way they do things. It used to be that you would submit a proposal, you'd say who you were, and people could say, oh, well, this is a person who has a good reputation and they publish things and they don't sit on their data, and let's give them time. But now they've actually gone to a new way of doing things where they don't know who's actually proposing. And so you write a proposal. You can imagine you put a lot of effort into writing a proposal to convince your peers that what you want to do is something that Webb can do and that it's something interesting to do. And then they rank the proposals, and then there's a cutoff, there's a finite amount of time, and then you're told whether or not you got time on the telescope. So we feel really fortunate to have gotten time in the first cycle. It was a hard thing to do. It was highly competed. And then there'll be other cycles and people will continue to compete. Sam.
What was it about your proposal that got you first in line, do you think?
It was a great proposal. So, many people got time in the first cycle, right? But many more did not. And yeah, I think we had a compelling scientific question. And what we proposed to do was to get at the real nitty gritty of why it is that we're seeing these differences and how to understand whether the differences are real or some kind of measurement error, something that we haven't been able to measure accurately until now. So we made our case, and the time allocation committee said, sounds great to us. And here's the
How
time.
long will it take you then to look at the data and come to a conclusion?
I think within a year, we will have pretty interesting results, but of course it depends on, any new instrument, in my experience, just takes a lot of time to learn how to deal with the systematics of the detector and the new parts that you didn't envisage would be a problem, turn out to be a problem, the things that you thought would be a problem turn out to be simple, and then you're training students and, mistakes happen and then you have to check them and recheck them. So it'll take quite a while. So, there are tens of thousands of stars, individual stars in these images that we have to measure. For the Cepheids, we have to find out how long, first find them, find the variables, measure how fast the atmospheres are moving in and out, measure their period, measure their luminosities, see whether or not abundance effects, the chemical composition of the stars is impacting their brightnesses. How is the dust impacting their, if it was easy, Hubble would have done it 100 years ago. But it's exciting because these measurements, we haven't been able to make measurements this precise before. So just like it's a key project, I feel really fortunate to have a career where I could use Hubble at the beginning and James Webb near the end of my career. It's just been really, I feel very fortunate. I know there was a hand, yet the person next to you, didn't she have her hand up? No? It was you. Okay, sorry, go ahead.
When you're using your on the web, space telescope, when you see, when you're looking at infrared light and you redshift, how do you know the difference between something that's really far away and just seeing this redshift light, as opposed to just something that's emitting in that infrared wavelength or maybe closer? Like, how do you make that distinction?
So we can measure the spectral features. So each chemical element has a unique signature, right? So it's hydrogen, carbon, nitrogen, oxygen. then the spectral line will show up at exactly the same position every time for that element. So when we're measuring redshift, what we see is a shift in those spectral lines, but the pattern is the same, except it gets stretched and shifted. And so these objects are not emitting in their so-called rest frame in anything other than what the elements will do. These are transitions, electrons, photons moving from level to level in a given chemical element. So that remains the same. What is different is the motion of the object.
What aptitudes does a young person need in the next generation of astronomy?
So the question is, what aptitude does a young person need to succeed in the next generation in astronomy? I'd say it's similar to what it took a century ago, but there are some differences. So I think it requires, first of all, mathematical ability. Passion, I would say, is another. It's a real passion to learn about the universe. It takes a long time to get a PhD in astronomy, and you have to go through lots of math and physics to get there. Creativity, and I think now what has changed is that the projects have gotten much bigger. So it was possible for a lone astronomer in Hale and Hubble's day to amass hundreds of photographic plates, and they owned them. They were all theirs, and that was the part of the universe that was theirs. Now, the single object kind of astronomy is a thing of the past, and the facilities have gotten much bigger. And so if you want time on the Hubble Space Telescope, you rarely will get it as an individual. You want to put together a team with different expertise, and you're going to be observing a much bigger area and many, many more objects than was possible earlier on. So a lot more teamwork, I would say, is required. Although, having said that, I think Barry and I prefer working in small groups. We have 6 people on our James Webb team. That's it. It's the 2 of us and a few students and 1 postdoc. So it's still possible to do things in small groups. But as I mentioned, the Reuben Telescope, the large synoptic survey telescope, it was called before, there are hundreds of people involved in these large surveys now. So it's a very different kind of science. So I think people have to find their own niche, how they work best. And of course, then there's theory too, people who don't do any observations at all, but simply are undertaking theoretical studies of evolution in the universe, how stars evolve, and so many different facets. And also instrumentation, of course, people building instruments. 2 more questions that you're telling me? Okay. Oh boy. Okay, I'm taking a lot on this side, so I'll go for you. Yes, you.
You're standing at you're building the next great telescope. What are some of the things from
Things from George Ellery Hale that are think big, make no little plans. So I think what I learned, and I think what Robin and Todd Mason captured so well on the journey to Palomar, is there are a lot of hiccups along the way when you're building big telescopes. And there were times as director where the Carnegie Institution gave me seed money, $500,000 when we started the project. When I stepped down in 2015, it had grown. We had legally binding commitments of $500 million. So this thing grew from a really small group of people to an international effort. But there were times at the beginning when the project manager would come to me and say, well, we have 3 more months of funding. We only had 3 people on payroll, but that was the end of the project if we couldn't pay them. So I would go home and think about, okay, now what? But I would remember George Ellery Hale. And I think unless you believe in a project, it's not going to happen. And we could have built a smaller telescope, but we won't learn as much. So you can put almost as much effort into something that's smaller, or you can take that next leap, and it might take longer. It will take longer, I think, almost by definition, when you're doing something that's never been done before. But if you have a vision, then you'll carry it out. So yeah, he was definitely for me a huge influence, and I, in my darker moments, would think, okay, just got to push through, and you do. Yeah, relevant today too. Yes.
So, what are some of the private public? How does it trickle down? When does it get released to the public? Is there like a large audience?
Yeah. So what happens to the data? Who owns the data? So if it's something like James Webb, of course, that's NASA funded, and there's some contribution from other countries too. And so that's taxpayer funded. So when you put in a proposal, right, it takes a lot of effort to put in a proposal, it takes a lot of time to analyze the data. So they give you a proprietary time. We'll have a year to analyze our data, but then it will go into a public archive and it can be accessed by anyone.
But for that year, nobody else has that.
That's right. That's right. It gives us time to do what we said we wanted to do, because otherwise other people could jump right on it and scoop you, and that's not the point of it, right? But the Hubble archive has turned out to be tremendous. And the science that's come out of it that was just never anticipated at the beginning or by the original proposals is just phenomenal. And we use it all the time. And you do get funding when you apply. If you apply to do a project with Hubble data from the archive, we'll also get funding to carry out that science. Yeah, so the ground-based telescopes are different in the sense that, at least to date, most of the money has come in the US at least from individual institutions, universities and private institutions. Now, in the case of Australia and South Korea and Brazil, that's coming from governments. And so that it's different in the case of the international partners. But what we're now doing is talking to the National Science Foundation to get the rest of the funding that's needed to complete the construction, because the partners themselves, there's just not enough money to go forward without the participation of the National Science Foundation. So in that case, once the National Science Foundation comes in, then it will be available to all astronomers. But if they were not to come in, then it would only be available to people at the institutions who have put in funding to make it happen. So it's a mixture. I was told that was it. Right? One more. Oh boy. Okay, right at the back.
Is the Hubble constant and if we're expanding into the universe, what are we expanding into? Confirmation background Webb data, see past that?
So the question is the Hubble constant, and what are we expanding into, which I talked a little bit about before. But so that the answer is, locally, the Hubble constant is a constant in the sense that if we make measurements here in the Milky Way galaxy and we look at our nearby neighbors, we see them moving away from us with a certain velocity. And at greater distances, they're moving with a greater velocity. So that's that relationship between velocity and distance that I showed you. If we were to move over to Andromeda or another nearby galaxy, we would measure the galaxies near us, including Andromeda. Andromeda, sorry, is a bad case. It's one of the handful of galaxies in the entire universe that's moving towards us. All the rest are expanding. So let's pick M33. Andromeda is M31. We'll pick M33, which is another galaxy in our local group of galaxies. So we would see the Milky Way expanding away, galaxies would be even further. So we would measure locally the same value of the Hubble constant. But the Hubble parameter, which it really is, does change with time with the expansion of the universe. So we also have, there's matter in the universe, and because of gravity, matter slows down the expansion of the universe. And also what we've learned in the last couple of decades is that there's another kind of energy, astronomers refer to as dark energy, that's causing the universe to speed up, to accelerate in its expansion. And so both of those, you have to take account both of those effects. For example, if you're calculating the age of the universe, you need to know how much matter there is and how much dark energy. So the Hubble parameter, we look as a function of distance or redshift, does change with redshift. I won't re-answer the question on what it's expanding into, but I'm happy to answer more questions if people have them. But I'll
People can come and talk to you. You're willing to stay.
Yes, but let me eat too. But yes, I'm willing to answer more questions. I'm happy to. Yeah. Okay.
All right, that was fabulous. Barry, did you like my introduction to you?
Yes.
I was also going to start on committee.
So I know the charge with change list on. I've been charged to start a running message. I forgot to do that too. Anyway. I got that.
It's not moving and I didn't realize that.
Two billion. Doesn't seem very expensive. Yeah.
Great to meet you. Just keep talking about it.
But you know what?
I am. And she's getting tired. Well, I would tell her when she has me sometimes. She gets tired. But she's sometimes tell you. She has to be encouraged. I didn't know that would happen.
We have two other camps running. The part where you would see. What's up.
We'll all be having dinner.
Yeah. Well, no, yeah.
Maybe take yeah. I don't know if it's possible. You have the 5G. Is on the rise in the Canadian. Yes. If you make 5G split up. It's the same house. Same house. We split it up.
We wanted to do each of one of the routers has its own password distribution. Sure. Right up in that direction. They just, you know, kind of like this. Yeah. So all the traffic, all the cell phones.
Oh, yeah, from 50 megabytes.
Future reference.
Yeah. And you're not going to get them to turn off the cell phone. You can't do it on an airplane.
No, that's a good. We do that.
You would make a lot more money,
Especially when I was
to, you know.
Yes,
It's not for this curve.
So we're just, I'll just have to change the password here. To the one 5G instead of something. Because we haven't done this.
If I do a third camera, iPhone, just don't put anything on it. Yeah, just Wi-Fi. So.
Maybe a higher level, we're to cooperate.
Let's say this week, that's it, the ways off.
Yes. Yeah.
You all are coming down to the deck.
No, sorry.
Let's go eat. Let's go. We'll get this lady down, get her some food. I don't know. So one last question, I'm sorry.
Thank you.
Thank you, guys. We'll see you later.
I'm fine.
Great.
Yes. Fine.
The Heliophysics Big Year is a global celebration of solar science and the sun's influence on Earth and throughout the solar system, and we want you to be a part of it. We challenge you to participate in as many sun science activities as possible, beginning with the annular eclipse in 2023 and ending with Parker Solar Probe's closest approach to the sun in December 2024. Space is increasingly part of the human domain. By studying the sun's influence in space and its interactions with planets, we learn how to better protect astronauts and robotic missions from space weather, and to develop technology that protects the very infrastructure we rely on here on Earth, such as power grids and GPS signals. NASA's Heliophysics division studies the sun's influence on everything in our solar system, from the very core of the sun to the very edge where the sun's atmosphere meets interstellar space. We have 20 heliophysics missions that are operational and 14 more under development. The Heliophysics Big Year will highlight the work that we're doing to understand our star and to mitigate the effects of space weather. The Big Year is a concept that originated with citizen scientists in the birdwatching community. During their Big Year, birders attempt to observe and study as many species as possible during a calendar year, and we are challenging you to do the same with our sun. During the Heliophysics Big Year, you will have the opportunity to participate in many solar science events, like watching solar eclipses, experiencing an aurora, participating in citizen science projects, and lots of other fun sun-related activities. So please be sure to look out for opportunities to be part of our Heliophysics Big Year.
How did it do? Everything work well?